So, partial derivatives in thermodynamics, our topic today. So let's do a little math review. Suppose y is equal to 3x and x is equal to 2u. Does specifying y automatically define x and u? If I know my y, can I solve for x? And if I know my x, I can solve for u, right? What if I specified my x? Can I solve for y? Yes, and I automatically know what u is also. I can solve for u, right? Similarly, if I specified u, then that automatically defines what x is, and that automatically defines what y is. In other words, what we're saying here, if these are the relationships between x, y, and u, then only one of these variables is independent. Okay, so this is you're looking at three variables, but you only have one independent variable. By specifying one, you specify all the other variables. Okay. Now, a nice thing about this one variable is you can apply in calculus what's called as a chain rule. Let's say y is equal to 3x and x is equal to 2u. What do I do to get dy? What is dy dx in this case? It's just going to be 3, right? What is dx du? It's going to be equal to 2. Okay. Now, if I want to know what dy du is, derivative of y with respect to u, what should I do? Well, I can substitute 2u for x, right? So I'm going to say y is equal to 3x and x is 2u, right? So I can say y is equal to 6u. So dy du is just equal to 6. Now, here's a chain rule. dy dx equals dy du. If I want to take the derivative of y with respect to u, I can first take its derivative with respect to x, then multiply that by the derivative of x with respect to u. That's your chain rule. You can think of it this way. It's as though you can just cancel that dx, you get your dy du. So I could have gotten this 6 right here this way. What's dy dx? It's 3, right? Multiplied by dx du. What's dx du? 2. 3 times 2 is 6. So this chain rule right here is a very important relationship involving derivatives that you need to be familiar with. Okay? Because we're going to be using that a lot. Now, what if y is a function of x? So when we say y is a function of x, instead of writing f of x, because we can be dealing with a lot of different functions, we just use, instead of f, the actual name of the function. So y, when you write something like this, you're saying y is a function of x. Okay? Y equals y of x. How does a small change in x affect y? So dy is equal, if I have a small change in x dx, then the corresponding change in y would be equal to something times dx. What goes here? Say dy is just how y is affected by x is given by the derivative. Derivative of y with respect to x times dx. And again, you can imagine that you're just canceling that dx right there. Okay? And this is a very important relationship to know. It's kind of trivial, but it will serve us well later. So let's say your x changes from x1 to x2. What's the change in y? Well, you can solve for y when x is equal to x1. You plug in x1, right? And you solve for y when x is equal to x2. You plug in x2. And then you subtract. That's your delta y, right? Y at x, actually, it should be x2 to x1, right? I'm sorry. Y final minus initial. But what if we don't know explicitly how y depends on x, but we might know, let's say, how the derivative of what the derivative of y is with respect to x? What we can do is this. You can say, instead of evaluating y at x2 and then evaluating y at x1 and taking the difference, I can say that delta y is just the integral of dy, which is the same thing as integral of dy dx, derivative of y with respect to x, dx, from x equals x1 to x equals x2. Okay, so let's have an example for that. Let's say y equals, let's make it easy, 3x squared. Okay, all right, so let's go from x equals 1 to x equals 2. What's our delta y? It's going to be 3 times 2 squared, right, minus 3 times 1 squared. So what's 3 times 2 squared? 3 times 4 is 12. 3 times 1 squared is 3. So that's 9, right? Let's see if I get the same thing if I use the derivative. What's dy dx? Derivative of y with respect to x is 6x. Let's see if I can get the same delta y. Delta y is integral of derivative of y with respect to x dx from x equals 1 to x equals 2, right? So that's the integral of 6x dx from x equals 1 to x equals 2. What's the integral of 6x? 6x squared over 2, right? Evaluated plus a constant, but since it's a definite integral, we don't worry about the constant. Integrated from x equals 1 to x equals 2. So that's 3x squared evaluated from x equals 1 to x equals. You can see it's basically the same thing, right? You get 3 times 2 squared minus 3 times 1 squared. So that's 9 minus, that's 12 minus 3, and that gives you 9. Okay? Now, what happens if you have more than one independent variable? So let's go. Then derivatives are no longer defined. You have what are known as partial derivatives. So let's say z is a function of x and y. So z, let's say, is the product of x and y. Does specifying x tell me what y is? It doesn't, right? I have to specify x and y to determine what z is. In fact, I can specify x and z, I can figure out what y is. So in this particular case, just the only thing we know about z, x, and y is they're related this way. We have two independent variables. So we can say here z is a function of x and y, or you can also say x is a function of y and z. Okay, but because what's x in terms of y and z? It's just equal to z over y, right? All right. So whenever you have more than one independent variable, you cannot have derivatives. You have what are known as partial derivatives. Okay. And so a partial derivative is simply of z with respect to y. Okay. It's just the derivative of z with respect to y if x were assumed to be constant, if you were to hold x constant. Now, I know that in your calculus classes you don't specify this, typically don't specify that down there. When you put that as a subscript right there, the variable that's indicated in the subscript means that variable is being held constant. Okay. Typically, you don't do that in your calculus classes, but in thermodynamics, you have to do that because we can be dealing with a lot of different variables, and we have to specify which variable are we holding constant, because we have generally we'll have a choice of what independent variables we want to deal with. Okay, so that's something you have to be aware of. That's what that notation means. So what would be the derivative of z with respect to y at constant x? Okay, I don't have an expression for z, do I? Okay. So let's have an example. I do have an expression right here. Okay, z is x times y. So if x were constant, what's dz with respect to y? It's like saying z is equal to 4y. What's dz dy? It's just 4. So whatever x is, the constant. So this is just going to be equal to x. Right? Similarly, the partial derivative of z with respect to x, if y were held constant, would be equal to y. So if you think of y this time as a constant, what's the derivative of z with respect to x? It's just going to be equal to y. Right? Right. Now, what if we make changes, small changes in x? That would be dx, and a small change in y, that would be dy. What would be the change in z? Well, you can just extend what we learned earlier. What did we say we learned earlier? If z is a function of, let's say, x, you say dz would be equal to what? Derivative of z with respect to x times dx, right? So if it's a function of x and y, you can just extend this. You can just say, so it's a function of x and y this time. Then you can just add derivative of z with respect to y dy. Except that in this case, since we now have more than one independent variable, instead of a derivative, what do we use? We use a partial derivative. So this is now going to be a partial derivative of z with respect to x, holding y constant. And this expression right here on the right is going to be partial of z with respect to y, holding x constant. Okay? So if x changes from x1 while y remains constant, what's the change in z? How would we answer that question? Let me rewrite that. So what did you say? Z is a function of x and y. Then dz, we say, is equal to partial derivative of z with respect to x dx. What are we holding constant here? Y plus partial derivative of z with respect to y dy. What are we holding constant here? X. Okay. So that's our expression. All right. So, how would you answer this question then? If x changes from x1 to x2 while y remains constant, what's the change in z? So you're being asked for delta z, right? How would we do that? Well, if you're holding y constant, okay? If you're holding y constant, then what does this expression reduce to? If y is constant, this is going to be 0 if y is constant, right? So what's your delta z then? You can just integrate. Z will just be, you can imagine z now is essentially a function of just one variable. Delta z would be the integral of dz, right? It's going to be the integral of the partial derivative of z with respect to x, holding y constant, dx, from x1 to x2. Okay? Okay. Let's just try a couple of examples. I want you to call out the answers to me. So let's say w is a function of r and s. Okay? So what would be my expression for dw in terms of changes in r and changes in s? Change in r and change in s. So what's the partial derivative that goes in the first blank? Me? Partial derivative. Okay, z with respect, not z, w. Partial derivative of w with respect to r, holding one constant. Okay. What's the partial derivative that goes in the second blank pool? W with respect to s, holding one constant. R. Okay? So Now, what if you have t is a function of x, y, z? Okay, this time you have three independent variables. So I'm going to say dt equals, so it's going to be affected by changes in x. So something times dx plus something times dy plus something times dz. Okay, so John, what goes in the first blank? With respect to x. So you have to specify y comma z down there. Okay. Okay. Joe, what's the next partial derivative here? With respect to y, holding what variables constant? X and z. And Catherine, what partial derivative goes in the last one? Partial of t with respect to z, holding what variables constant? X and y. Okay? So you can extend this to more than just two variables. Right. Now, we need to be able to relate partial derivatives. Okay, so what we're going to try to do now is derive some relationships between partial derivatives. And the reason we want to be able to do this is that some partial derivatives are easy to measure and some variables are easy to control in the lab. Okay, some variables and some partial derivatives are easy to measure, easy to control in the lab. Some are not. So what's the value of being able to relate partial derivatives? Well, if there's a partial derivative you want and it's not easy to measure in the lab, you may want to relate it to something that's easier to measure. Okay? So let's say you have a system that's described by variables x, y, what else? R and z and s. Okay? But only two of those variables are independent. So you pick your independent variables. Let's say we pick x and y as our independent variable. It doesn't really matter as long as the variables you pick are actually independent. Okay, so let's say we only have two independent variables, although we have a lot of variables we can use to describe our system. In thermodynamics, you might have to deal with like H, U, entropy S, U is internal energy, H is enthalpy, G is Gibbs energy, A is Helmholtz free energy. We'll talk more about those later. Okay, and then you have pressure, volume, temperature. So you can see you have a lot of these variables. Okay, but if you have a closed system, you have thermal and mechanical equilibrium, fixed amount. Okay, so if you're dealing with changes in pressure and temperature, for example, you might be dealing with two independent variables. Okay, so let's see what happens here. Okay. All right. First of all, why don't you give me the expression for dz in terms of dy and dx? Sydney, z is a function of x and y. So z is a function of x and y. So dz is equal to something times dx plus something times something. What goes in this first parenthesis? Of z with respect to x, holding what variable constant? Okay. And the second one, what variable are we changing here? Y, dy. So what partial derivative goes here? With respect to y, holding what variable constant? All right, dx. Okay. Fix that up. All right. So now, what if I wanted to know what the partial derivative of z is with respect to r if we are to hold x constant? Let me derive that expression based on this. Okay, so I'm going to try to relate it to the derivatives from this expression. So partial of z with respect to r at constant x. Okay, and now, oops. take partial derivative of z with respect to r. I'm going to color code this so it's easy. What variable are we holding constant? Oh, let me rewrite this. Okay, partial derivative of z with respect to r. Okay, holding what variable constant? X. That's what I want, right? That's the derivative that I want. Okay, think of it this way. You're just going to hold x constant, okay, and you're going to divide this expression right here by dr. So I divide through by dr, so the right-hand side becomes what? Basically what I do here is, okay, I copy this derivative right here, partial of z with respect to x at constant y. But now this dx that I have, I'm going to divide that by dr, okay, while x is being held constant, so I can say that that's what? Partial of x, and we'll show that later. We'll cancel that out because that's 0, right? So partial derivative of x with respect to r, holding x constant, okay? Plus, what do we have here? Copy this derivative, partial of z with respect to y at constant x. And now I imagine dividing this dy by dr at constant x. Okay, so partial of y with respect to r. Again, in this case, we're going to be holding x constant. Can you see what I did there? I just divided the left-hand side and the right-hand side by dr at constant x. And so when I divided dx by dr at constant x, I end up with the partial derivative of x with respect to r constant x. When I divided dy by dr at constant x, I have the partial derivative of y with respect to r at constant x. Okay, so let's simplify this. What can we do to simplify this? What's the change in x if x is held constant? So, see, this one's going to be not changing. If x is not going to be changing, then dx is going to be 0. So this term is just going to drop out, right? So this is just going to be 0. And so what do we have here? Partial of z with respect to r equals partial of z with respect to at constant x is equal to partial of z with respect to y at constant x times partial of y with respect to r at constant x. Does this look familiar? It's just like the chain rule that we had for one independent variable, right? In this case, we just chose the second variable x to be constant. So you'll notice in this relationship, the variable being held constant is the same. So you can apply the chain rule to your variables. Okay? So that's one identity you need to be familiar with. Okay, let's see what happens now if you want to take the partial derivative of z with respect to z at constant x. Okay, let's do this next one. Okay, so let me write this one. This is going to be partial of z with respect to, what was it? R at constant, no, what was it? Partial of z with respect to x at constant y, with respect to y at constant x, times partial of y with respect to r at constant x. Okay, let's look at this second one right here. Now we want partial of z with respect to z at constant x. So now I want to change this. rest of this. Okay. So this time we want partial derivative of z with respect to z at constant x. So we're holding x constant. So what do? We just divide the expression on the right through by dz at constant x. So call these expressions out for me. What's this first expression here? Partial of z with respect to x at constant y. What do I multiply it with? Partial of x. You just keep that dx right there. Z at constant x. Okay? Plus, okay, pull this one is partial of z with respect to y at constant x. What goes here? Partial of y with respect to z at constant x. Holding x constant. Okay? So you're just dividing through by dz at constant x. Okay? Now let's simplify this. What do we get? This is equal to, so partial of z with respect to z at constant x is equal to, okay, is there anything we can do here? Again, at constant x, this dx is just going to be 0, right? So this thing drops out, so it's just this term on the right. So we have partial of z with respect to y at constant x times partial of y with respect to z at constant x. Is there something else we can do to simplify it? What's partial of z with respect to z? What's the ratio of the change of z to the change of z? This is just equal to 1, right? So what we can say then is, okay, I can rearrange this. I can say partial of z with respect to y at constant x is the same thing as 1 over partial of y with respect to z at constant x. Does that make sense? It's like saying dx dy, if you flip it, then you take the reciprocal. Right? So, okay, so that's an important relationship to know, because sometimes it's easier to take the derivative of y with respect to z than taking the derivative of z with respect to y. So if you end up with an expression, you're having a hard time getting the derivative of y with respect to z, the derivative of z with respect to y, but you can easily get the other derivative and take the other derivative. One application of this that you might encounter would be like in your van der Waals equation, P equals nRT over V minus NB minus AN squared over V squared. Okay? If you are going to take the partial derivative of V with respect to, let's say, T, that's going to be hard to do because you have to solve for V, and you'll have a cubic equation, third order polynomial in V. But you can easily solve for T in this case, right? You can say T as a function of V, and so partial of T with respect to V would be easier to solve. Let's just say this is at constant pressure, okay? And constant number of moles. So this might be harder to determine from this expression, but the derivative of T with respect to V would be easier to do. Okay? So that's our second relationship that we're trying to do. So we're saying that this is equal to 1, and that's just And from this, you can show that partial of 1, z with respect to y at constant x is equal to 1 over the partial of y with respect to z at constant x. That's called the inverse relation. Okay? So let's take a look at this third derivative right here. Let's see what kind of identity, what kind of relationship we can get out of that. Partial of z with respect to x at constant r. Partial of z with respect to x at constant r. Alright, so now I'm going to say partial of z with respect to x at constant r. So what should I do? I'm just going to divide through by dx at constant r. So, John, what's the first expression? Okay, just copy that first derivative right there. So, partial of z with respect to x at constant y, and then with respect to x at constant r. So you can see we're just dividing through by that. Same expression basically, right? Plus, okay, Joe, what's the next pair of derivatives you have to write? Okay, partial of z with respect to y, holding what constant? X. Okay, so you just copy that first expression right there, and then the second one you divide by dx at constant r. So, okay, partial of y with respect to x, holding what constant? R. Okay. So again, you're just dividing through by dx at constant r, and let's see if we can simplify this and get another identity involving partial derivatives. So what can we simplify? What's dx over dx? That's just 1, right? And there's nothing else to simplify. So I can say then that partial of z with respect to x at constant r, I'm just going to copy that, equals partial of z with respect to x at constant y plus partial of z with respect to y at constant x times partial of y with respect to x at constant r. So this is another identity you need to be familiar with. Okay? You really shouldn't try to memorize this. What you can do is try to work backwards. Okay? First of all, what's the value of this identity? Okay. Here's a derivative of z with respect to x at constant y, and here's a derivative of z with respect to x when you're holding some other variable constant, in this case, r. The value of this relationship is that if you want to know, if you happen to know the partial derivative of z with respect to x holding y constant, okay, but you wanted the derivative when some other variable r is being held constant, this is the relationship you need. These are the two other partial derivatives you would need in order to figure out the derivative that you want. Okay, and sometime later this semester, when we try to solve for, we try to derive a generic expression for Cp minus Cv, okay, you will have an expression where you would need to relate partial derivative of u with respect to t at constant pressure, okay, I'm sorry, from the partial derivative of h with respect to t at constant pressure. No, sorry, not that. Somewhere in the derivation, okay, you'll be needing to get the partial of derivative of u with respect to t at constant pressure, okay, and you'll be able to express that in terms of partial of u. You need to know what that is from partial of u with respect to t at constant volume. So if I have that, okay, what derivatives do I add back here? So here I have the partial derivative of u with respect to t at constant volume. This is something I might easily be able to do. This is an or measure in the lab. This one is not something I can easily measure in the lab, maybe. Let's just say. But if that were the case, okay, actually, this is just an expression that comes up in our derivation for Cp minus Cv. But if you have partial of u with respect to t at constant v, what other two derivatives go in here? Let's work backwards. Okay. So where must have this expression? Let's go back. So this, if I go back to my du, okay, and I have that derivative right there, partial of u with respect to t at constant v, okay. What's my d over here? D something. dt, right? Partial of u with respect to t dt. So my variable being held constant over here is v, right? So what's the other d that I have over here? This is going to be dv, right? So what's this partial derivative I have here? Partial derivative of u with respect to v dv, right? What variable am I holding constant here? T. All right, so you can work backwards. So what goes in here and what goes in here? What did I divide it by? The expression by dt at constant p, right? So this one stays here. So that's partial of u with respect to v at constant t. And what goes in that second parenthesis? This one. So partial of v with respect to t at what? At constant pressure. And so that's the relationship that we have. Okay. For partial of u with respect to t at constant volume, from that, if you want to change that to partial of u with respect to temperature at constant pressure, you're going to have to get these derivatives. What's the nice thing about these derivatives over here on the right? They deal with volume, temperature, and pressure. Those are things you can easily measure in the lab. Easily measure, easy to control. So if you know this, okay, and you can easily measure these other two derivatives, then you can figure out the third derivative. Okay. So that's your third identity. And then another identity that we can use, let me start with a clean slate here. Okay. All right. So the last derivative that we need to show here would be partial of z with respect to x at constant z. Okay? With respect to x at constant z. So partial of z with respect to x at constant z. All right? So you divide through by dx at constant z. So Catherine, what goes here? holding y constant times okay, what goes in the next blank, in the next parentheses, Sydney, with respect to y, holding x constant times with respect to x holding z constant. Very good. Let's see if we can simplify this. What's partial of x with respect, let's see, anything here that we can simplify? What's partial of z with respect to x holding z constant? 0. So this left-hand side is 0. Okay, and how can we simplify this first expression right here? Dx and dx cancel out, so this will just be partial of z with respect to x at constant y plus, and this one doesn't have anything you can simplify. So this is partial of z with respect to y at constant x times partial of y with respect to x at constant z. Okay? Now, I'm going to try to put all of these derivatives into a product. So, I'm going to move this one over to the left. Okay? So that's negative of partial derivative of z with respect to x at constant y equals partial of z with respect to y at constant x times partial derivative of y with respect to x at constant z. Okay? And what I'm going to do now is I'm just going to divide both sides by partial of z with respect to x at constant y, so that I get rid of the derivative on the left side. So partial of z with respect to x at constant y. And so what do I have? So this left-hand side now becomes this negative 1, right? Now, I want all my partial derivatives in the numerator, so what should I do? If I want to move this up there, what should I do? I just flip my x and z over here, right? So I can say that, okay, let me rewrite all of that. Partial of z with respect to y at constant x, this is your numerator. Partial of y with respect to x at constant z, times, if I flip this, what do I get? Partial of x with respect to z at constant y. This whole expression is equal to negative 1. So that's another identity you need to be familiar with. Okay? Now, look at, it's not very hard. It's actually one of the easiest identities to remember. Look at this. Okay, you're holding x constant here, right? And then you now take the derivative of y with respect to x, this time holding z constant, and then over here, so this one tells you what variables to do next, and this one, the partial of x, the next expression here would be partial of x with respect to z. So you're just switching roles for x, y, and z. Okay? So you take the derivative of z with respect to y, holding x constant. So you hold x constant first, okay? And then you hold z constant, and then you hold y constant. Okay. Let me see if you can apply that. I'm going to give you different letters. So what if I were to do this? partial derivative of P with respect to T at constant volume times what derivative must be equal to -1. Assuming I only have two independent variables. What goes in the next parentheses? T with respect to volume, okay, at constant pressure. What goes in the next one? Okay, so the next one you have volume with respect to pressure. Okay, so partial derivative of volume with respect to pressure, holding what constant? Temperature. Okay. And the value of knowing this is, as we shall see later, okay, this is something that you can easily calculate from a quantity called alpha. This is called, so this is not alpha, okay, this is in fact 1 over alpha v, where alpha is a quantity, a property called the isobaric expansion coefficient, thermal expansion coefficient. So alpha is something you can easily look up. So this is 1 over alpha v, and this is going to be negative kappa v, and kappa is something else that you can easily look up. So this is something you can use to solve for partial pressure with respect to temperature at constant volume. Okay, so this is a useful identity to have to know. So let's go ahead and summarize all of these. This is a summary of the derivatives that we derived, in just using other letters. But so what's this first one? That's basically the chain rule, right? The second one, that's the inverse relationship. The third one, that's the I think here Atkins calls it the permuter relationship. Okay, you just cycle through z, y, x, and then you have y, x, z, and then you have x, z, y. Okay, and then the last one right here is what? This is what would be the derivative of z with respect to y, holding x constant, if you know that derivative with s, some other variable s being held constant. Okay? So that's the extra stuff you have to add to the other derivative to get the derivative you want. All right. So what sort of partial derivatives are easy to determine, easy to measure in the lab? One is called the isobaric expansion coefficient, alpha. Okay? And if you know alpha, then you can, if you multiply alpha by the volume, and integrate from temperature T1 to T2, V alpha times dt from T1 to T2, you get the change in the volume of your system at constant pressure. So based on this, what derivative is equal to V times alpha? This must be integral dt. What are we looking at here? Change in volume, right? At constant pressure. So change in volume at constant pressure. And what variable are we changing? Temperature, so it's partial of V with respect to T at constant pressure. So that must be V alpha, that derivative right there. Okay. In fact, that's the definition of alpha. Alpha, okay, is equal to 1 over V times the partial derivative of V with respect to temperature at constant pressure. How do we interpret what alpha is? Look at the expression here. It tells you the relationship, the ratio of the change in volume to the change in temperature. Okay? Change in volume divided by change in temperature. So if I were to plot volume versus temperature at constant pressure, what's this partial derivative here? That's just the slope, right? The slope at a given point is dv dt. Multiply that by, divide that by the volume at that point. That would give you your alpha. So you can define alpha as the fractional change in the volume. See, it's the ratio of the change in the volume, okay, the change in the volume to the current volume, to the actual volume. So it's a fractional change in the volume resulting from a temperature change. By how much does the volume change? By what fraction does the volume change for a given change and for a unit change in temperature while you're holding pressure constant? Okay? So that's the definition of alpha. And so what would be alpha for an ideal gas? Let's see. So we said alpha is equal to 1 over V times partial of V with respect to T at constant pressure. It's isobaric because we're doing constant pressure. So for an ideal gas, what's the value of alpha? Well, what do we know about volume and temperature and pressure for an ideal gas? PV equals nRT, right? So for V, in terms of pressure and temperature, what do we get? Volume equals nRT over P. Okay, if I were to hold my pressure constant, nR and P are going to be constant, what's my derivative of V with respect to P, to temperature? nR over P. Oops. Okay, so what's my alpha? 1 over V times partial of V with respect to T at constant pressure. So that's 1 over V times nR over P. What is 1 over V times nR over P? So what's nR over PV? 1 over temperature. Okay. So alpha for an ideal gas is just 1 over T. Whatever the temperature of the ideal gas is, its alpha is just 1 over T. T being in Kelvin. Okay. And is that unit consistent? What should be the unit for alpha? You have a volume unit here, a volume unit down here, so the volume units cancel out. What's the unit for alpha? A reciprocal temperature unit per Kelvin. Okay. So that's the unit for alpha. What about a van der Waals gas? How much time do we have? It's 9:30. Okay, so how about we make this your homework for a van der Waals gas? Okay, what's alpha for a van der Waals gas? You're going to have to do this expression for a van der Waals gas. P is nRT over V minus NB minus AN squared over V squared, right? Okay, you're going to need partial of V with respect to T at constant pressure. Okay, and you're going to have a hard time solving for V in terms of T because you have powers in V here. So use the reciprocal identity. Okay, so it would be easier to just get 1 over partial of T with respect to V at constant pressure. Okay, so let's make that your homework. If you want to use MathCAD for that, feel free to use MathCAD.